Good morning. My name is Jason Weber, and I'm an engineering lead on the Internet Explorer team at Microsoft. And for the last 3 years, my team and I have been focused on making Internet Explorer fast. And we've learned a lot about web performance during that time. And we're going to share that with you today. We've learned a lot about the browser runtime and how the browser runtime works internally and how to optimize that runtime for current and future web performance trends. And we'll give you an inside look at that today. We'll also talk about how you can optimize your sites and Metro-style applications for that browser runtime. Now, the first thing you'll notice is that I'll be presenting today from within inside Internet Explorer with a web app. This is actually an HTML5 application that runs today inside IE8, IE9, and IE10, and also runs as a Metro-style application and works great in other browsers and on other platforms as well. You'll see that as I resize my window, all of my content is going to slide around dynamically. If I open the developer tools, you'll see that all the source code is available. Nothing's obfuscated. You can take a look at exactly what we're doing here. Now, I'm going to go ahead and close the developer tools, maximize my window, and refresh this web application. And you'll see that I'm dynamically loading 241 different slides that we're going to go through today. And you'll see that I've loaded over 18 megabytes of content in just a couple of seconds. And as I browse through my slides, you'll see that it's extremely fast and responsive and snappy to move between the content. So let's go ahead and get started. Now, throughout the week, you've seen this architectural diagram many times. Today, we're going to be focusing on two pieces of this diagram. The first are traditional web applications that run inside Internet Explorer, as well as other browsers, such as Firefox or Chrome or Safari. It's just the web. It's just the standards-based web, and all of the performance techniques that we'll talk about today apply to standard web applications. We'll also be talking about Metro-style applications, which are also just the web. So all of the performance techniques that we talk about today, with a couple of minor exceptions, apply to Metro-style applications as well. So a quick show of hands. Who's here today because you want to build faster websites and faster web applications that run across all standard browsers? Okay, everyone in the room. Who's here today because you want to build faster Metro-style applications for Windows 8 and the platform? Almost everyone as well. That's great. So my goal today is that you'll leave with two things. The first is an understanding of what makes a website or web application or Metro-style application fast. And my second goal today is that you'll leave with specific things you can do. In fact, 50 specific things that you can do to improve the performance of your sites and apps today. Let's start with a couple of numbers. So this is session 386. This is a 300 series level talk, which means it's going to be extremely technical. We're going to talk about everything from HTTP and networking to HTML and CSS and JavaScript and compilers and JITs and everything in between. So we're going to be going very broad and very deep at the same time. Another important number, 30. 30 is the number of slides that the Microsoft marketing team recommended that we presenters use in the course of our presentations this week. 241 is the actual number that I'm going to be using. So I'm a little off. Trust me, you would not believe how worried they were when they first saw this presentation. They didn't think I'd be able to get through all the content. And so a couple of key things here. We're going to be going extremely deep technically, and we're going to be covering a lot of content today. This session is being recorded. My recommendation is that you just sit back, relax, don't try to take notes, just enjoy the session, and find a couple of key performance tips and tricks that will apply to you and take those back with you. And then you can go through the full list of 50 sometime on your own in the video itself. So let's start with a test. How much do you guys know about web performance? I mean, everybody raised their hands that you're building websites, you want to make your websites fast, so you must have spent some time thinking about web performance. So I thought we'd start with a scenario. I'm from Seattle, and like many of you, I needed to somehow get down to LA for this conference. And I needed to purchase a round-trip airline ticket. So I did a little test. I went to 6 of the most popular travel sites on the web based on unique users: Expedia, Orbitz, Travelocity, Yahoo, Priceline, and Kayak. And I measured how long it took to load the home pages of these different sites. And if you think about kind of the home page for these travel sites, they're all very similar. They all have edit fields where you can type in where you're coming from and where you're going to, and checkboxes whether you're doing round trip or one way. They also have common elements like kind of logos and banners. They'll also have kind of very interactive real-time data on them about where's the cheapest current flight coming from, what deal can we offer you. They display advertisements, they're doing analytics. They're all doing the very same thing. And so you would expect them to kind of have about the same performance, wouldn't you? Or same kind of architecture. So I dissected them, and I'm going to call them site 1 through 6 here. I kind of anonymized it a little bit because I don't want to poke at different sites and point out who's doing things maybe well and who can improve a little bit. But let's take a look at a couple of statistics or kind of data points around these sites. And actually, I'm going to hit F11 and go into full screen mode so the chart's a little bigger. And so the first kind of dimension we're going to look at here is kind of the total kilobytes of data that are downloaded when I went to these sites. And you'll see it ranges very significantly. If we look at site number 3, there's only about 450K that were downloaded, whereas site number 6 had 2.2 megabytes. That's a factor of 4 or 5. If we look at the number of elements in the fully constructed DOM after the page is loaded, you'll see the significant variance here as well, between 600 and about 3,000 almost. And again, a factor of 5. If we look at the number of CSS rules that are in the fully rendered page, again, between about 500 and 1,700, factor of 3. If we look at the number of external image files that are downloaded, we'll see there's about 30 on the low end to close to 100 on the high end, factor of 3. If we look at the number of lines of JavaScript that are downloaded, and these are what we call F-lines or formatted lines, so we kind of factor out the minification and we reformat the code so we're comparing apples to apples. You'll see that the number of lines of JavaScript ranges between about 8,300 and close to 30,000. Right? Very significant difference in the way that these sites were architected and the libraries and the frameworks that they chose to use, both on the client and the server. Okay, so we've looked at 6 sites, and we've looked at some characteristics of those sites. So which one's the fastest? Site number 2. Well, okay, a guess for number 2. The correct answer is site number 4. Site number 2 is often the most common answer. And that's because people look at the total lines of JavaScript, and they assume that the amount of JavaScript in your page is directly correlated to how fast your page loads. Now, this worked out really well for me, because the site that happened to be the fastest actually had the most amount of JavaScript. So it really helps kind of reinforce the point. Okay, so that was an interesting kind of data point. Which one was the slowest? Everyone's going to be hesitant to guess now. It's not as obvious as you thought it might be. Most images. Okay. So most images was site number 3. The slowest was site 5, which actually had the lowest number of images. So this worked out doubly well. So I'll talk about these sites in more depth in a little bit. But I wanted to start with really what is web performance? Right? We all have our own definitions of web performance. And it's really when does the user perform an action until when does those results kind of occur on the screen? And there's 3 key factors to web performance. The first is network bandwidth, network connectivity. It's a bottleneck in many cases for web performance. The second is CPU. How efficiently can the CPU and the web runtime and your code perform operations? And the third is the GPU. And we'll talk more about this in a few slides, but the GPU is critical to web performance. These 3 dimensions are the 3 dimensions that as web developers we have to think about to improve the performance of our applications. Whether that's a classic website, a Metro-style application, and whether that web application is running on a mobile device or a powerful desktop machine, these are the same 3 dimensions that we have to focus on. On the Windows platform, you can measure this inside Internet Explorer, as well as other browsers that run on the Windows platform through the Windows Performance Toolkit, which is a free download from Microsoft, part of the Windows SDK. It's fantastic. If you haven't used this, I would strongly encourage you to download it. It's actually not that overwhelming. At the bottom of the slide here, I link to a blog post that walks you step by step how to go and measure these dimensions across all browsers in your apps on Windows. Now, I'm going to be showing a lot of charts today. All of the charts I'm showing you, all the data I've collected comes from these tools. So there's no magic here. You can go and measure this yourself on Windows Vista or even Windows 7 and, of course, Windows 8. So let's take a look at a CPU chart. This is a CPU chart for loading one of the most popular sports sites on the internet. One of my favorite sites, which is how I picked it to look at today. And let's look at what's happening. So again, we're just focusing on the CPU right now. So when I go to type in a URL or click on a link, the first thing that happens is the browser issues a document request. And it's going to download that root HTML markup. And you'll see a little spike of activity on the CPU because we just sent that network request. But then the next thing that happens is the browser basically sits there idle. We're not doing any work because we don't have that document yet. The CPU is idle, the GPU is idle, the network is essentially idle. Somewhere in the internet, this request is going. And then a few hundred milliseconds later, usually between 200 and 400 milliseconds later, that markup comes down, that HTML markup. And the browser starts to parse that markup. So you'll see a little spike of activity. And as we're parsing that markup, we're going to find sub-resources that need to be downloaded. CSS and images and JavaScript, and we're going to quickly issue those to the network. But relatively soon after that, we're going to be, we'll have parsed the entire document, and we're going to be idle again, waiting for those sub-downloads to occur. And so we kind of have this again, lull in CPU activity before finally we hit a point where we have enough resources that we can fully utilize the entire CPU. Now, this is a dual-core machine. And what you'll see is that the web platform can really only fully utilize one core of the machine. The web platform is inherently single-threaded. Now, there are some features of the web platform that can be parallelized, things like image decoding or JavaScript memory management, or web workers allow you to parallelize within your applications themselves. But for the most part, your web application is limited to one core of the machine. And so when you see here kind of at 50%, the web platform and this web app are fully utilizing the entire CPU. Now, again, at some point in time, we start fully processing content because we have enough content streaming in off the web that we can start parsing the CSS and the script and the images and everything. So we're using that core. But then oftentimes in the middle of a web page, you'll see again a lull in CPU activity, a drop. This is because the app may choose to do something. It may choose to dynamically add more resources to the page that have to be downloaded, and so we're blocked waiting for those resources to come down. In this case, it was actually a synchronous XHR in the middle of page load that was occurring in the application itself. And then after that block kind of is freed, then we can start processing content again. And you'll see in this case that for the next couple of seconds here, the CPU is pegged, and then finally the content is displayed to the screen. And from the user's perspective, often at times at this point in time, it feels like the app is loaded, but there's still a bunch of activity occurring on the CPU until finally the page finishes loading. Now, there's 4 key dimensions here that I want to talk about. The first is what we call time to glass. This is the time from when the user performs their initial action until the content is displayed to the screen. This is an extremely critical aspect of web performance because we want the perception that our sites are loading as quickly as possible. We can still be doing work behind the scenes after the content hits the screen, preparing for the next set of user actions, but we want to get that to the glass as soon as possible. The second line down is what we call lapsed page load time. This is the time, how many seconds or milliseconds it takes from when the user clicks the action, clicks on the link, until the page is fully loaded and the CPU acquiesces. So this is elapsed page load time. Now, within that elapsed page load time, there's 2 key metrics, and these are the third and the fourth here. The third is CPU time. How much during that page load time was the CPU actually busy? And then the fourth is idle CPU time. How much time was the CPU just basically wasted? And so as web developers, as HTML5 developers building this new class of Metro-style application, our goal is to take these 4 aspects of web performance and push them as far to the left as we can to make our actions instantaneous. Okay, so now that we kind of understand that there's the CPU and the GPU and networking involved, and we really have to kind of look at the CPU time, we need to drive down the CPU time. The question is, well, where does this CPU time go? Right? Because it's not JavaScript, or it may not be JavaScript we learned, it may not be images. So I thought I'd start with an architectural kind of diagram of the browser, or a web platform. And this is true across all web platforms. We have different names, we have different architectural boundaries, we have different kind of code names for our subsystems, But all standards-based web platforms inherently do the same thing. So if you were to look at an architectural diagram of another web platform or another web browser, it'd look very similar. And it starts with networking. There's a core networking subsystem that is responsible for downloading resources from the network, or possibly caching those resources locally and providing a backup to the web application. Kind of the next subsystem that's offered encountered is kind of a core HTML parsing subsystem that takes all of your markup, parses it into internal data structures, and represents it as kind of a DOM. There's a CSS subsystem that's also responsible for kind of parsing the CSS itself and building internal data structures of the formatting information. Most browsers have a collection subsystem, which you could think of as just a bunch of metadata about your site that's going to be referenced during the runtime. Of course, JavaScript is key. There's a JavaScript subsystem that's responsible for everything from parsing that JavaScript to generating bytecode or intermediary languages to executing that JavaScript. Most browsers have a boundary between their JavaScript engine and the browser itself. Something that's, we often refer to this as the marshalling tier back and forth. And there's time spent in this communication tier between a browser and the core web platform. Of course, there's the DOM, and there's time spent performing DOM interactions, manipulating nodes, looking up elements in the DOM itself. There's a formatting subsystem, which is responsible for taking all of your markup and all of your CSS and overlaying them on top of each other and formatting your page. There's a block building subsystem. CSS is inherently a block-based layout model. It's a bunch of rectangles, and so you have to build these blocks every time you're about to lay out the page. There's a layout system that takes the blocks and figures out locations and z-orders. And then finally, the content is displayed to the screen. Okay, this is key. These 11 subsystems are key because I wanted to go back to the 6 travel sites that we looked at earlier and kind of show you the breakout where the time's going. So what you'll see here on the left is the number of milliseconds it took to load the page. And this is a scale between 0 and 3.5 seconds, or 3,500 milliseconds. And this was on a relatively high-speed network. It was 3 megabit network. And you'll see for site number 1, kind of color-coded where the time goes. And so you'll see at the bottom is the light gray time. This was the amount of time where the CPU is essentially idle, waiting on the network network activity to occur. You'll see as we work our way up on the kind of the site number 1, we're going to look at the subsystems in the same order that we just did. You'll see in light blue at the bottom the HTML subsystem. You'll see for site number 1 a lot of time spent in JavaScript, the JavaScript subsystem. But then in purple you'll see kind of the marshalling tier. As we work our way up through green and orange, you see the layout system, and finally in purple you'll see the display subsystem. Now, a key point, for each one of these sites, the bottleneck, the reason that it's not as fast as it could be is different. For site number 1, it's primarily JavaScript, and it's blocked on JavaScript performance. For site number 2, it's networking and possibly displaying content to the screen. You'll see those are the largest pieces where the time is going. And if you look at something like site number 5, you'll see it spends a lot of time in all of these subsystems. The tips and tricks that we're going to talk about during the remainder of the session are all about decreasing your CPU time and increasing your parallelism in all of these subsystems. If we were to average those 6 travel sites together, you see something like this. This is where the time goes. About a quarter of it is idle network. You're just blocked, waiting for the network. You can see that JavaScript is about 20% of it. Layout is a large piece of it, about probably 18% itself. And then painting to the screen in purple is about 25% of it as well. This is why the GPU and the display are so critical to web performance. It's not just about fish. It's about real-world performance as well. Now, the question I often get is, okay, these are travel sites. What about these highly interactive AJAX sites that I want to build, or these metro-style applications? So we took 25 of the most complex AJAX applications on the web, sites like Gmail, the Facebook wall, and we profiled them as well in interactive scenarios. And let me show you the breakout there. So again, these are the travel sites. Here's the distribution for those highly interactive AJAX sites. And I'm going to jump back and forth. Now, one thing that often surprises people is they think that, again, here's travel sites. Here's the interactive AJAX sites. They associate JavaScript performance with AJAX. They think the faster my JavaScript engine, the faster my AJAX application is going to be. But that's actually not the case. For AJAX applications, the most important kind of aspect of performance is that pipeline between formatting to layout to block building to displaying content to the screen. JavaScript actually plays a smaller piece of the puzzle. Okay, so let's jump into the 50 performance tricks. Again, everything we're going to talk about today is about decreasing that CPU time, increasing parallelism, and improving your performance. Now, the 50 tricks we've organized into 6 different principles. Really, at the end of the day, these are the 6 principles I would like you to walk away with. And the first principle is to quickly respond to network requests. So let's take a look at that. If you think about it, when the user types in a URL or the user clicks on a link, you want to get the content down to the user as quickly as possible. And the first step in that is avoiding redirection. Now, if you're familiar with 300 redirection, what happens is that the browser issues a GET to a URL or a URI, and that is going to return a response. Now, that response may redirect to another site or another URL. Now, this redirection can cause 200 to 250 milliseconds of delay in your web applications itself. Now, if you think about it, it's like, okay, that's 250, 200 milliseconds. That's not a big deal, right? The redirection gives me some convenience on the server side. But if you think about it, that 200 milliseconds is about 10% of the page load time. So you want those requests to go directly to the destination themselves. Now, this is the point in time where some people often get up in the presentation and they're like, I know all this. This is the basics. I'm going to go see another session. Well, it might be basic, but 63% of the top 1,000 websites in the world contain a 300 series redirect. 63%. 63% of those sites could improve their performance by about 10% just by not using a redirect. In that same context, avoid meta refreshes. Right? We've all used meta refreshes because we're lazy. We just kind of drop in an HTML page because we don't want to do a redirection, and we say, if anybody ever hits this, redirect to another URL. Of all of the pages on the internet, of all of the pages in the Bing and Google search indexes, 14% of them contain a redirect. It's just completely inefficient. Okay, so after we've avoided our redirection, we want to minimize the time spent on the server to get that initial HTML document back to the browser. We want to get the content to the browser as quickly as we can. So we want to respond to those requests. So oftentimes in a web application, when that request goes to the server has to do work. And people often forget to measure this, but that server might be going and talking to a user database trying to figure out who is this person, or where are they coming from, or I'm going to log a bunch of analytics about this user before I even get the data back to them. And in many cases, it might hit, especially with internal applications, it might start hitting databases trying to calculate data. All of this time on the server blocks the browser from moving forward, blocks your web application from running. So you want to minimize your time there, especially in the initial set of requests, and get your content back to the user as quickly as possible. When appropriate, use content distribution networks. I'm sure many of you are familiar with CDNs. But if you think about it, let's say we're in Atlanta, Georgia. We have a user in Atlanta, Georgia. And they're talking to a server in Redmond, Washington. Well, that request isn't actually, if it was going straight across the country, it'd be about 2,500 miles. But it's actually not. It's actually circling around through kind of lots of different routes, oftentimes going through California on its way up to Redmond. And it's about a 3,500-mile one-direction trip, 7,000-mile round-trip request. That's about 250 to 300 milliseconds today on high-speed networks to make that round-trip request. This internet thing is amazing. And with CDNs, you can geolocate your data very close to your user, especially your static resources. You can use services like Azure, or you can use services like the Amazon or Google services to geolocate your data and provide those resources very quickly to the user, minimizing the time spent on the wire. You want to maximize your concurrent connections. When people think about networking, they often think about kind of one pipeline going to an individual server. They're just kind of round-tripping data between the client and server. But browsers can make 6 concurrent connections to a server and will download those content in parallel. But browsers will actually do that on a per-domain basis. So if you distribute your content across multiple domains, you'll actually be able to download 12 or 18 or 24 resources in parallel. So if we think back to those images in some of those sites that we were just looking at, if those images would have been distributed across 6, 7, 8 domains, and geolocated to the user, that content could have been there within a couple of hundred milliseconds, and if you think about it, kind of decoded and deserialized in parallel and available to the web app immediately. When you're making these connections, make sure to reuse them. Don't send connection closed. You'd be surprised how many frameworks on the web today send connection closed. In fact, some of the default configurations for servers like Apache will send connection closed in many cases. So you want to minimize this. Let the browser reuse the connections that are established. Know your servers. As web developers, it's really easy to link to some cool script or use somebody else's server or service. As you're doing this, really think about what is the performance of that other person's server, or what is the kind of service level agreement that you might have with that other server in terms of performance. You're only as fast as your weakest link. And it's surprising, oftentimes even some of the largest sites on the web, they don't realize the impact of their weakest link. So as you're looking at your performance data, really understand where your resources are coming from and how that's impacting performance. The second principle, okay. Principle 1 was all about quickly responding to network requests, getting the data back to the client as quickly as we can. Number 2 is about minimizing the number of bytes being downloaded. The fewer resources you download, the better. So really take a look at all of your resources and minimize the number of bytes that you need to download. The average website today downloads 777K worth of data. And if we look at that, it's actually distributed across these types of resources. So the vast majority of that is images, followed quickly by JavaScript and Flash content. The fewer bytes you download, the better. And the best way to download fewer bytes is to gzip your content. Now today, a lot of us get this for free because of the servers that we're using and the browsers that our customers are accessing from. But just as a refresher, the way that gzip works is when the request is made, it sends to the server, as part of the header, it says that I support gzip. I support this encoding. And the server can automatically send back an encoded, a smaller version of that content. And when it gets to the client will then decode that and expand that to the full-size version of the content. Now, again, a lot of servers give you this for free, but a lot of people unintentionally, accidentally, turn off some of these decoding techniques. And so really make sure, look at the, kind of using tools like the Windows Performance Toolkit, you can make sure that all of your content is gzipped. Now, the best way to minimize the number of bytes downloaded from the network is to not download anything from the network itself. And in the Metro-style applications that you're building, we strongly recommend that you package all of the resources you need for your application inside of the AppX package. And then that way, your web application or your Metro-style application doesn't have to hit the network at all. It doesn't have to go to your server. It just pulls those resources locally from the package. And so they're immediately available to the web application itself. Now, you can choose to architect your applications in different ways. You could choose to architect your application really just as an iframe or a small wrapper around a web-based application that you might have. But that's probably not going to provide the performance that your customers are going to need. So really think about how can you architect that application and that initial experience based purely on local resources. Now, people often say, well, that's the AppX package. That's my Metro-style application. What about IE? Or what about a browser? Or what about dynamic content where I don't want to package up today's news headline inside of my AppX package. I want that dynamic every day. And for those scenarios, you can use an HTML5 app cache, which is a new capability available in IE10 and Metro-style applications and competitive browsers that enable you to cache all of your content locally. And the way that app cache works is your web application, the first time it's accessed, it goes out to your web server, and it downloads the data from your web server directly, and it puts it inside of the app cache. So really the content is coming into the app cache itself, not into the browser. And then the app cache provides that to the browser. So your web application is really just pulling its resources from the app cache. At a later point in time, you could choose then to update your application to v2 or v3. And what happens is the app cache pulls that from the web. It dynamically pulls down v2 of the app, or v3. It persists it inside the app cache, and then it serves it up to your application. So once you've implemented HTML5 app cache, your app doesn't have to be aware of kind of the network. It just dynamically pulls the resources and they're available. Provide cacheable content. So even if you choose not to implement HTML5 app cache, make sure the content you do provide is cacheable. And so when you initiate your request, make sure that your response specifies an expiration period. The browsers will then persist this in what we call kind of our temporary caches, and we'll serve those back up without having to hit the network. Again, just minimizing the number of bytes. Now, oftentimes people will say, but I don't know if I'm going to change an aspect of my site. I may change my logo. I might change my user interface. I might change this other aspect of my site. And so they're often hesitant to mark some of their content as cacheable. In those cases, you can use what are called conditional requests, where you can mark your content as cacheable, and you can kind of essentially say, if the content has been modified since this date, send a new version. If it hasn't, just use the version from the cache. So it's a great way to kind of separate out your application resources that aren't going to change very often from your dynamic content and still give you safety fallbacks. Make sure that you cache your data requests. Today on the web, less than 1% of the actual data requests themselves, data requests such as XML HTTP requests, are actually cached in the browser. But this data often doesn't change. If you go, and we've performed some kind of interesting analysis on this, but in many cases over the course of a day, about 95 to 96% of those XHR requests actually serve back the exact same data. That means that 95% of the time, you're just making a call, and you're just downloading the exact same data, which costs server resources, it costs network time, it costs local resources. So mark your content as cacheable. Most frameworks out there today have a mechanism for you to do this quite easily, just adding something like a cache true property. Use standard file capitalization. Again, this one often surprises people as well. But if you think about a scenario where we might, in part of our page, we'll download an icon, and then we'll use lowercase. In a later part of our page, we'll download what we think is that same icon, but we'll use title case. And then what I call careless developer case, where you just kind of type it in quickly. Now, the server may actually resolve all of these to the exact same file and serve you back that same file. But from the web platform's perspective, these are three separate files. These are three separate files stored in the local disk. These are three separate network requests. These are three separate requests that are competing for the resources that we talked about earlier. And so if you standardize on file capitalization, it can, in many cases, significantly improve performance. OK, so principle number 2 was all about minimizing the bytes that we're downloading. Principle number 3 is about efficiently structuring our markup. So now that we're efficient on the network, we need to make sure that the HTML and CSS that comes back is efficiently structured to be quickly rendered to the screen. This is an Internet Explorer 9 specific and IE 10 specific best practice. In fact, this is the only one that is IE specific in the entire deck. But we recommend that you load your pages inside IE in the latest standards mode. We're committed to compatibility, and we continue to render content inside IE in legacy modes. You can render IE5 and Quarks mode and IE7 content in the browser itself in a fully compatible way. In fact, we still have most of those code paths in the browser itself. And so for your content, just make sure that you're using standard HTML5, or make sure that it renders in the latest standards mode. It's always going to be the fastest mode inside IE. Now, on occasion, you might have, for example, an internal line of business application that you still want to render in IE7 mode or IE8 mode. You can do that by specifying a meta tag in the page itself that says, hey, I don't want to update this application. Just go continue to run this in IE7 mode. The recommended way to do it, though, is to actually put that in the header itself. If you think about it, again, the browser downloads the content from the web, and it starts parsing that initial HTML. So we're parsing away in our latest standards mode, which is where we render the content by default. When we encounter this tag, what happens is we kind of say to ourselves, oh, this needs to go through an older pipeline inside of IE. And so it resets all the state. It moves from the HTML5 pipeline back up to the IE7 pipeline and starts reparsing that entire document again. If your content is in the header of your HTML markup, we can push that page into the IE7 pipeline immediately. So this can save you about 10 to 15 milliseconds, depending on your page and your scenario, if you're continuing to render content in legacy modes. Always link your style sheets at the top of the page. This is an important one for a scenario that's often referred to as the flash of unstyled content. If you think back to the web 10 years ago, we often had these experiences where content would kind of stutter in. You sometimes see a flash of a white screen or a flash of a side. Now, it still happens today, but to a much lesser degree because people are kind of a little more sophisticated about how they structure their markup. But when your CSS is in the head, the browser is going to synchronously block painting content on the screen until this CSS information is down. The other thing the browser is going to do is this CSS information that's in the head of your page is the most important, one of the most important aspects of your app because we need this before we can display a formatted app on the screen. And so it's going to issue these network requests first. And it's going to try to get this down, this content down before, say, images, which can be asynchronously brought down later. Never link your style sheets at the bottom of the page. I often receive emails from people really frustrated with their user experiences, where things are stuttering in, where they feel like it takes a really long time to load their page. Over half the time, it's because they have their CSS in the wrong place, and it's often at the bottom of the page, and so it's being downloaded after all these images and after all these asynchronous JavaScripts that really just don't matter to their performance. So always put your CSS at the top. And when possible, avoid using the @import mechanism for hierarchical style sheets. @import synchronously blocks the creation of some internal CSS data structures and painting to the screen. Now, browser runtimes try to work around this, and we have caches and fallbacks and misses, but really the best thing for you to do is just avoid the pattern altogether, and you'll be guaranteed better performance. In that same regard, avoid embedding your styles inline in your page itself. I know it's very tempting, especially when you're trying to fix a little bug or just make one little thing appear differently. But when you have your style information in the page, it causes a context switch. The browser has to switch between the HTML parser and the CSS parser, and it's constantly moving back and forth. And that invalidates things, even little things like the CPU cache. I've been on pages where they've used entirely inline styles, and it's just by moving to a single CSS file at the head that can be parsed in one chunk, they've improved their performance 15 to 20%. Only include the necessary styles that you need in the page. Many sites have a very large CSS file that they include across all their pages, which contains essentially a bunch of global style information. And many, we can all be lazy at times, and so we'll all kind of just append a little style information into a style sheet where it may not be appropriate. So in this case, you can imagine a site where all the styles for on the home page are in the same file, as well as all the style information for, say, the content pages. Some of the top news sites in the world use this pattern today. In fact, one of the top news sites in the world has a CSS file with over 4,000 rules in it, of which only about 5 to 10% are used within a single page. Now, what this means is that the browser has to go and parse and create all of these complex data structures for all the styles that aren't needed. And if you remember that formatting step where I talked about how we take the DOM and we take the formatting and we match them together to get the resulting page, that formatting is slowed down because of that. Now, always link your JavaScripts at the bottom of the page. It's a very common best practice. That way the style, kind of the visuals of the page can be downloaded and constructed first, and then your JavaScript can come along and manipulate the page how it would like. Always avoid linking your JavaScript in the head of the page. This is especially true on older browsers. Now, there's kind of a really interesting tidbit here. And the reason for this is that if you think back kind of 5, 10 years ago, browsers are a little more sophisticated today, but the pattern still applies. But 5 to 10 years ago, if you had JavaScript in the head of your page, that JavaScript could do something like a document.write and rewrite the markup itself in the content of the page. And so the browsers would synchronously block on that JavaScript, download it, parse it, construct whatever AST model they had, execute that JavaScript, and then continue parsing the rest of the page. And in the same context as CSS, avoid inline JavaScript. You have the same types of context switching issues that you have with CSS. And in fact, to even a larger degree, because with modern browsers, which are trying to build much more efficient dynamic type systems and JIT code at runtime, they may not have all the information they need to JIT the most effective code at any point in time. So make sure you're putting all of your CSS in external files. Don't litter it around. Now, on occasion, you might have to put JavaScript in the head of your page. For example, if you're using some type of a CRM system or you're using a hosting service, and that's where the only place you can put it. In those cases, you can add the defer attribute onto your page, which will help a little bit. The best practice, though, is to really just put it at the bottom of your page. And ideally, with it at the bottom of the page, use the async attribute. And what this tells the web platform is that we should download this JavaScript asynchronously and execute it asynchronously. And then you can use patterns in your JavaScript to just dynamically attach to the page or your application after it's loaded. Make sure that you remove duplicate code. This one often gets a chuckle, right? This is kind of an extreme case where we have 2 instances of jQuery in our application. 52% of the pages on the web have duplicate code. 52%. And I'm not talking about, we've all copied a little string copy routine or a snippet of code around. I'm talking about large swaths of code where there's more than 100 lines of identical code that instantiate identical types in a page. 52%. Standardize on a single framework. There are a lot of great JavaScript frameworks that are on the web today. A lot of them really do the same thing, so there's duplication of functionality. And you may not be using that duplication of functionality, but the browser or the web platform still has to download all of those files, has to parse the markup, it has to construct the JavaScript. It doesn't know it's going to be executing, so it might even be generating native machine code for each of these JavaScript libraries. So really just pick a framework, one that you like, use that consistently. It will very significantly improve performance. And don't include scripts to be cool. There's a lot of great little scripts out there. The Facebook like buttons, the analytics, the monitoring scripts. It's really easy just to, include one script file and then have some amazing thing happening behind the scenes. Well, all of that script is running in the context of your page load. And guess what? These scripts are not altruistic. They're not trying to minimize their performance or do things asynchronously after your page loads. They're competing with you for resources during that page load. Okay, principle number 4. Optimize your media usage. So again, we've got extremely fast network, we're responding to our network requests quickly, we're minimizing our bytes, we've got our markup efficient. So now we need to optimize the media that we include inside of our markup. Going back to this image, you'll see that over half the bytes downloaded today on average are images. The average number of images in a website today is 58 across the top 100,000 websites. So you want to be very careful to avoid what I call death by 1,000 images. If you start cropping up above 20, 30 images, you probably have some performance impact to the number of images that you're downloading. So really avoid too many images in your site itself. And especially avoid this pattern. We see this a lot today on the web with social network where you have 50 different little social networking icons along the bottom of your page. And oftentimes these social networking icons are coming from 50 different servers on the web. So really be careful of that pattern. When possible, use image sprites. And I'm sure many of you are familiar with image sprites. But on the left, we have kind of scenario 1 where we have 6 images. And each of these images is a separate image in the page, which means it has to be downloaded. You have 6 connections to download these images. They're all being downloaded in parallel. 96K of total images are being downloaded. Scenario 2 on the right, I've taken these 6 images and I put them into a single image strip. And I can use CSS or another mechanism to just lay out the appropriate image on the site. You'll see that I have one image, one connection to download that image, and I'm only downloading 21K. So by efficiently composing my media this way, I'm actually improving the performance of kind of all of the principles that we've talked about. And I'm especially improving the performance on the client itself. One dimension that we haven't touched on is the GPU and graphics memory. On the left, I have 6 different images, each taking up their own memory on the GPU. On the right, I just have one. When you create your image sprites, though, make sure that you create them by hand. Here's an image sprite that I took these little images, and I ran them through a tool that generated an image sprite for me. And you'll see that there's a lot of wasted space in this image sprite. Wasted space that's taking up bytes over the network, memory on the GPU itself. So make sure you create them by hand in a very efficient way. The other thing you'll see is that this image didn't realize that my 2 Microsoft logos were the same bits. And so it just took the 2 Microsoft logos I included and stuck them into the image strip in random locations. When you're using, in terms of image formats, when you include your images, there's a lot of philosophical debate around formats, but I just recommend that you default to PNGs for everything. For everything. PNGs are the most efficient format on the web in terms of kind of the balance between compatibility, encoding size, CPU encoding time, amount of memory required for the kind of decoding of the image itself, some of the best compression rates in terms of compatibility. Just default to PNGs. Occasionally you might want to use a JPEG for photographs or JPEG XR for really high resolution photographs, but default to PNGs. And make sure when you include your images that you include them at the native image resolution. In this markup, we'll see we're including an image that's 500 pixels wide by 400 pixels tall, but we actually only use it at 50 by 40. And so we're scaling it down 10%. Just scale it down on this, in an image program and download the appropriate image size. Again, it kind of saves you on all of those dimensions that we've been talking about. When possible, replace images with CSS3 gradients. Now, as web developers, we always have these cases where we have like a 1,200 pixel tall image by 1 pixel wide to fake out a gradient or some pattern, and then we stretch it and skew it, and we get the right result on the screen. With modern CSS3 capabilities, we can do all of this in markup. We don't need to be downloading images. We don't need to be taking up all that memory or those bytes for images. And so you can use, in this case, just the CSS3 gradient to create the exact effect that we like. And with gradient stops, there's really nothing that you can't do in CSS. Use the border radius to create kind of rounded corner effects. You know, we've all have built 9 grids before, where we have 9 little images that kind of represent different quadrants of kind of a rounded corner effect. And so using the border radius property of CSS3, we can do that straight from markup. And you can put border radiuses on anything, on divs, on CSS3 elements, on canvases. It's great. And in that same context, you can use CSS3 transforms to move and rotate and skew all of your content on the screen. So there's cases where you had to have 3 or 4 different images that represented kind of an effect. You can now do purely from markup. For really small images in your page, you might consider using data URIs for those small images. And the way the data URIs work is you just include an image tag, as you normally would. But then, instead of including a link to the image, you put the data colon kind of attribute in there, which indicates that you're about to include a base 64 encoded string. And there are lots of tools on the web that will take a PNG or a JPEG and give you this string back. But you just include this directly in your markup, and then the browser doesn't even have to download a separate resource. When you're using SVG, which is a great technology, avoid complex paths, though. Especially if you look at the SVG that's often generated from a tool like Illustrator, it's ridiculously complex. This takes a long time for the browser to kind of download and parse and construct. And so generate your SVG by hand. It's much more effective. When you're using HTML5 video, use image previews. If you don't specify a preview image for your video, the browser has to download that video and kind of figure out what the first scene or screen of the video is, or the first frame, and display that to the user. When you include a kind of a preview, the browser will just down the preview, download that, display that to the user, and then we won't start downloading the video until appropriate. I strongly recommend using HTML5 video over some of the runtimes that are out there today, from a pure performance perspective. Now, this is one that often surprises people because there's a perception that some of these runtimes are faster. In the 3 years that I've been working on IE performance, I have never seen a case where one of these runtimes can do something faster than HTML5 and IE9 or modern browsers. And there's a kind of a core piece that people often forget about here, which is that when these runtimes are running, they're competing with the machine resources, with the web platform itself, and oftentimes slowing down that overall web application. And so some of the benchmarks that you see on the web, the way that those benchmarks work and the way that they make these runtimes look faster is because they take over the entire machine resources. And so it looks like those runtimes are running really fast, but they're blocking the web platform from running. They're blocking the user from interacting with your site. And in many cases, you're going to be using very rich media in your applications. And when possible, proactively download that media before you need it. Don't wait on the user to click a button to download it. Just go ahead and issue a request, cache it locally, either in your app cache or in the temporary cache, And then the next time the user clicks that button, the media will be there. Okay, fifth principle, write fast JavaScript. Modern JavaScript engines are amazing. The world is completely different than it was 5 years ago. 5 years ago, JavaScript, it was okay, but it really wasn't fast. Today, all JavaScript engines are generating native machine code. They're essentially compilers. In IE9, we only have a compiler that generates native code. And so let's take a look at an example. On the left, we have some, you can picture this in C or C++, but some native code that goes across, it loops through 10 billion times an integer and does some math. So you think of this as largely 10 billion adds with some wrapper code around it. On the right, we do that same thing in JavaScript, which is a dynamic language. So let's say we were to call that function 999 times with a value of 999. And we were to do that math 10 billion times. In C++, that would take about 40 milliseconds. That's incredibly fast, right? There's 1,000 milliseconds in a second. It's ridiculous. JavaScript a few years ago, good luck, right? It might return in 10 minutes or 15 minutes. But with today's modern engines, it can do that same math in 200 milliseconds, a factor of 5. And some people will, there's the C++ guy in the back of the room. He's like, haha, right? We're 5 times faster than you are. It's like, well, if you're doing 10 billion adds in 40 milliseconds and you need that level of performance, you're probably doing cryptography, and C++ is probably the right language for you. If you're building most real-world applications in the world, JavaScript is incredibly fast for those today, in most cases. Now, there's one catch. There's one catch that I wanted to talk about today, and that's integer math. So the top, we were just passed in an integer to this function, 999. Well, let's take a look at what happens when we pass in a float. So you'll see that we pass in 999 divided by 2, which gives us a float. C++, that's still 40 milliseconds. We're in a static language. It knows the type. It can compile very efficient code. In JavaScript, that's 1,600 milliseconds. It's scaled down. Now, I won't go into the details why, but script engines use a technique called type specialization to actually know that something is an integer. And we do a lot of tricks internally inside the scene, behind the scenes. And so in your web applications, when possible, use a technique like math.floor or math.ceil that takes a float, turns it back into an integer, and you'll maintain your performance. You only have to do this in a couple of key places in your app. You don't have to do this everywhere. It's just those key spots where really tight loops are occurring, and your performance can go through the roof. Now, make sure to minify your JavaScript. Most of you minify today are familiar with the technique, but essentially, you take your JavaScript, you remove a bunch of unnecessary characters, you rename some variables, and you end up with a smaller amount of JavaScript that you have to download. Now, there's a hidden benefit to this, which is runtime performance. Because you're working with smaller, tighter code and smaller variable names, it's actually more efficient for the runtime to look up a lot of these variable names. And so you get both download performance as well as runtime performance. It's a great technique. You should also initialize your JavaScript on demand. Don't load your entire JavaScript library and framework when your page loads. Do a lot of things dynamically. In this case, we just have a variable for something like changing a user tile, which a user doesn't do very often. If that function is called, meaning if the user actually wants to change their user tile, inside that function itself, we just check a variable to see that that's code, the code's not actually loaded, and then we go and load the code. And so there'll be a slight delay when the user actually clicks to change their user tile, which doesn't happen very often, but the web application itself is considerably faster. Minimize your DOM interactions. Be smart about those interactions. In this case, we have a variable that first calls document, and it actually crosses over to the DOM and gets the document. It then takes that and calls body. So after it's kind of returned back to the script engine, it passes back over to the DOM and gets the body, then it comes back and it goes back and gets all, and it's constantly going back and forth between the script and the DOM. In this case, we've actually done 15 DOM lookups. What we could have done is we could have cached some of these. We could have cached document. We could have cached body. We could have cached left side, and minimized our DOM lookups. And then that way, our code doesn't ever have to leave the script engine. The built-in DOM methods are always faster and more efficient than anything that you can write in JavaScript. So when possible, make sure that you're using these and not any third-party libraries or your own code for these interactions, like navigating trees. So in this case, we're just going down to first child, or next sibling. And when you need to kind of query for a large number of DOM elements, we recommend query selector all. It's faster than any script-based mechanism that you can find. Inner HTML is a great way to construct your pages. There's a lot of debate around this on the web and kind of semantic value of constructing your pages one node at a time. But a great way is just construct your markup. It's a single string, pass it to inner HTML, and that can be 10 to 15 times faster in real-world patterns than actually constructing the DOM yourself. And in that same context, batch your markup changes. So when possible, batch those strings together, or batch your DOM changes together into one manipulation of the DOM itself. And maintain a small and healthy DOM. I recommend that maintaining a page of about 1,000 elements. It will greatly improve your performance. A couple last ones. JSON is always faster than XML for data. XML is a great data format, don't get me wrong, but JSON from a performance perspective is much more efficient. So use that when possible. And then use the native browser JSON methods. Use regular expressions sparingly. Again, a great programming technique, but regular expressions take 5 to 6 milliseconds oftentimes to construct and match complex trees. That's 5 to 6 milliseconds that could be often done inside of a string concat in a few 100,000 cycles. Okay, the last principle. 3 or 4 more things that we wanted to cover today real quickly. So the last principle is to know what your application is doing after it's loaded and running. And that starts with understanding JavaScript timers. JavaScript timers, of course, are programmed through set timeout, set interval, and what you end up with is a pattern where you're getting callbacks every n number of milliseconds. Most applications on the web today have 10 to 15 timers running at all times, and about half of those are what we call dormant timers, where they've been lost. And so make sure you don't have any timers or sequences that are running that aren't impacting the performance of your app. And combine your application timers together. In this case, we have a set interval that's running at 6 milliseconds, one that's running at 10 milliseconds, and one that's running at 50 milliseconds. Do we really need 3 separate timers running? Or could we have a single scheduler in our app and concatenate these together? Align all of your timers that are doing graphics and visual work to the paint beat of the display. Now, all of the displays that I've seen around the room and that are up here are running at 60 hertz, 60 FPS. That means the screen is updating 60 times a second. If we have a set interval that's running at, say, 10 milliseconds, that means our JavaScript is trying to update that screen at 100 times a second. Just a ton of wasted, unnecessary work. So an easy way to improve your performance is to look at all of your set intervals today that do graphics work and change them to 16.7. With Internet Explorer 10 and Windows 8, you can use a new API called Request Animation Frame, which is a standards-based API that's broadly available in Chrome and Firefox now as well, that will actually give you a callback when the browser wants to paint. So you don't have to worry about doing this on a timer. So use Request Animation Frame. And with that, we've covered the 50 performance tips and tricks that the IE team would strongly recommend that you consider to improve the performance of your apps. Now, I just want to touch on 2 things really quickly. The first is the 6 principles to remember. Let's go through those again. So quickly respond to network requests. Minimize those bytes that are downloaded. Efficiently structure your markup using the techniques that we talked about. Optimize your media, write fast JavaScript, and know what your application is doing. Let's go back to those travel sites really quickly. Travel site number 1 includes a significant amount of code that's not actually executed at page load time. You'll see site number 1 has all this time in JavaScript. This is spent trying to outsmart the JavaScript engine. What they do is they download about 4,000 lines of JavaScript code, and their JavaScript code reflects on itself and dynamically creates more JavaScript code. Right? They save their network time. You see site number 1 has the smallest network time because it actually didn't download that many bytes. But then it spends all this time in the JavaScript engine trying to be smarter than the browser. Don't try to outsmart the browser. Write efficient JavaScript. If we look at site number 2, it didn't do 1 redirect. It actually did 2 redirects. There were 300 milliseconds of time spent redirecting to redirect. Just go straight to the source. If we look at site number 5, look at all that time in site number 5 spent painting to the screen. This is the course of a page load. This is 3.5 seconds. It painted to the screen over 50 times in the course of a page load. It could improve. Site number 5 here could actually be the fastest site on this list if it just painted 3 or 4 times. That formatting loop that we talked about, the layout loop, the painting loop, could easily be decreased to just 3, but through a little more efficient markup, and be the fastest site here. So again, all the measurements that I showed today were collected with the Windows Performance Toolkit. You can go and download this. You can use tools like Xperf and some macros that we have in the blog post to very quickly kind of measure your own sites. I would strongly recommend it. Again, remember that it's all about the network, the CPU, and the GPU. It's not just about any one of these dimensions. It's about all of them working well together. I'd encourage you to go and play with the IE test drive. We have lots of cool demos up there that use some of these patterns to do really efficient things like whiz around images on the screen, to display lots of fish, to show that your browser can speed read. So with that, I'll be taking questions in the booth for the next couple of hours. I'd love for you guys to stop by. I'd be happy to look at your sites with you, and we can profile them and talk about how you could improve your performance individually. Thank you today. Please, my last slide, please submit feedback on the sessions. That helps us make sure that we're building the right conference for you in the future, and helps us make sure that build is as great as possible. So thank you.